Ух, кажется, я наконец в зуме, правильно?
Да, слышно.
Да, все, я отключил звонок в Телеграме, потому что в Zoom
Ух.
появилось
Значит,
дублирование.
трансляция запущена. Вы нас видите, мы вас, по крайней мере, слышим.
Мы только пока не видим.
Не видите? О, Господи.
Нет.
Так, следующий шаг.
Сейчас, но нужно виртуальную камеру в Zoom, иначе, не иначе плохо, потому что будет нельзя одно устройство, одну камеру и в Zoom, и на YouTube.
Так, значит, что нужно делать? Вот я в окне зума.
Да, нужно в OBS виртуальную камеру запустить. Сейчас я посмотрю. Так, в Ютубе, если что, там транслируется рабочий стол пустой.
Так, это самое демонстрация экрана, расширенные. Что там, материал со второй камеры, да?
Да.
Что вы видите? Что-нибудь видите?
Видим действительно камера на заднем фоне, а практически все место занимает рабочий стол.
Это сейчас. А где только я не вижу.
В OBS нужно выбрать камеру.
Видим что-то понятное, что-то странное.
В OBS нужно выбрать камеру. И там других источников не должно быть видео. Просто камера. Там сцены есть, там должна быть сцена, которая просто камера. Можно попереключать сцены, посмотреть, что будет в OBS. Потому что сейчас проблема из-за OBS, я думаю. Потому что мы в Zoom и на трансляции одно и то же. Так, отлично. Вот сейчас, да, но виртуальную камеру можно включить в OBS.
Хорошо.
Теперь вот этот, источник нужно убрать. Да.
Откуда он взялся? Как его убрать?
Как сцена называется, которая сейчас?
Камера.
Камера, тогда этот источник можно просто удалить, я думаю. Потому что в камере должна быть только камера. Так задумывалось.
Где вы, откуда, как вот это?
Вот там список источников, шестеренка, удалить источник. Потому что, не должно быть в камере ничего другого. Это, если нужно будет, сделаем другую сцену, чтобы не путались.
То вот этот источник удалить?
Который окно, да, потому что камера, если сцена называется камера, я думаю, логично, что там была только камера. Одна.
Да, нужно вернуть только мышкой его на серединку. Вот.
Да, эту как камеру вернуть на весь экран.
Все. Теперь все хорошо? Можно начать?
Только давайте камеру чуть пониже, а то доска левая не видна.
Она лежит... нет, она не лежит.
Не, просто чуть пониже опустите, да. Как обычно. Вот теперь замечательно.
Боря, у меня последняя просьба. Это самое.
Да.
Сделайте, пожалуйста, скриншоты участников.
Хорошо, ага.
Так, теперь и на Ютубе то, что надо.
Хорошо.
Здесь,
друзья, несмотря ни на что, мы справились с помощью Саши и Бори. Okay, it's great to start the talk. I must say that we have a long-running seminar called Vassiliev Invariants, Combinatorics of Vassiliev Invariants, and I have to say that this seminar is now will not be running anymore. And this is almost the last issue of this seminar, because it will reborn next year under different name, Combinatorics of Invariants. But since it's still Combinatorics of Vassiliev invariants, my talk is surprisingly will be devoted to Combinatorics of Vassiliev invariants. So I will be speaking on weight systems, and this is indeed the main topic of the title. So I will speak on weight systems, and this is a continuation of the talk by that was done by Joke Young. In February. So I will recall, let me first introduce the plan of my talk. So first I will recall the results of that talk. So we have indeed a weight system, and we introduce a weight system, a special weight system, which is defined on the space, on the collection of chord diagrams. And it's called universal GL weight system. It takes value in the ring of polynomials in an infinite set of variables that are denoted by C0, C1, C2, and so on. It has the property that it's multiplicative. And also, it's a weight system, so it satisfies the four-term relation. And the idea to construct this weight system is to extend this to a larger set of objects. Namely, we associate the value of the system to any permutation. So that chord diagrams, or to be more precise, the arc diagram is considered as a permutation on the set of its ends, which is involution and involution without fixed points, the product of independent transposition interchanging the ends of the chords. And on the space of permutations, we define this universal polynomial by some system of recurrence relations, and they have the following properties. So let's compare these to particular Lie algebra GLN. Then we have the corresponding weight system associated with the Lie algebra GLN. And it takes value in the center of the universal enveloping algebra of GLN. And this invariant is a specialization of this particular one, which takes C0 to the dimension n of the corresponding matrices. And CK goes to the standard Casimir generators, which are has the following form: E1 sum over I1 IN IK EI1 EI2 I2, EI3, EIK, EI1. It's known that these Casimir elements generate the center. Moreover, the first n capital Casimirs are independent generators of this center, and all other Casimir elements could be expressed as polynomials in these generators. So this is a ring of polynomials in the first Kn Casimirs. Cn. And the remaining generators also belong to the center and expressed as polynomials in this one. So this is, I will recall the definitions later, but this was explained in the talk of Zhoke. And now, since that time, Sergei Lando suggested to Zhoke consider the case of Lie superalgebras GLMN. And what kind is there is an analog of this situation for the weight systems associated with the Lie algebras GLMN. And then
Lie superalgebras.
Lie superalgebras GLMN. I will recall the definition later, but the theorem, which is also to Zhoke. So my role is just I polished a little bit the proofs, but the theorem essentially says that again the universal GLMN invariant for GLM and invariant associated with Lie superalgebra GLMN is obtained from the same, the same universal invariant where we should put C0 is equal to the difference, the super dimension, m minus n. So in this case, we specialize n to a positive integer, the dimension n. But here it happens that the specialization with negative C0 is also makes sense. And we have the corresponding specializations, and Ck are Casimirs, the standard Casimirs. And also, these Casimirs generate the center, but it's not, the relationship is slightly more complicated. It's not isomorphic to polynomial ring, but however, one can take first m plus n elements as the generators, then the remaining Casimirs are expressed not as polynomials, but as rational functions. But still we have this situation. So this is, I will discuss this statement and this proof, and all the definitions related to this case and the previous one will be done in the talk. So this is the plan. So in a sense, when we pass from the case of GL to the case of superalgebra GLMN, we have no new informations. Have got no new information. Okay. So now let me pass to the definitions. Well, I don't know. No idea. You mean the consequences, the corollaries? No. No. Yeah. Даниил, а можно попросить мел принести на 412 на этом самом, на доске? Цветной. Okay, let me now recall, explain the definition. So if you have a chord diagram, first of all, we represent this chord diagram by an arc diagram. We take some point, cut and unroll the chord diagram and turn it into arc diagram, something like that. So this is an arc diagram with 6 chords. Then what we do, we take the associate with each chord an index I, J, K, and then in the case of GLN, no, sorry. Now, what I said that I interpret this as a permutation. So I represent a permutation as the corresponding
Just put 1, 2, 3, 4, 5, 6.
I represent a permutation as a corresponding directed graph, which shows the action of the permutation. The arc connects the starting an element with its image. So in this case, I said that this is a involution. So instead of each arc, I put 2 chords in opposite directions. So this is a graph associated with a chord diagram.
Yeah,
Then,
but just put 1, 2, 3, 4, 5, 6, so that we will see what this permutation is.
so,
Yeah.
so we have cycle 1, 4, 2,
2, 6.
2, 6, and 3, 5.
Yeah.
And here we have 1, 2, 3, 4, 5. 1 goes to 3, goes to 4, goes to 1. One cycle, another cycle is 2, 5. Then we put here an index on each, associated index with each arc. I, J, K, L, I, J, K, L, M. And then to each vertex we put the generator of the corresponding GLN. And the indices are the incoming arrow and outgoing arrow. So here I put EIJ, here I put ELM, so here I put EJK, then EKI, and then EML. and sum up over all possible collection of indexes E, I, J, K, L, M. And this is an element that we are computing. This is W GLN of D.
Максим, не очень хорошо видно. Можешь повторить еще раз? В каком порядке перемножаются?
Примножая слева направо, индексы, которые я ставлю здесь, это номер входящий над входящей стрелкой, номер над выходящей стрелкой. Здесь входит стрелка с номером И, выходит стрелка с номером G, поэтому я пишу И с индексами ИЖ. Ну и так дальше.
Понятно.
Сейчас, а я пропустил номера стрелок. Это что?
Мы расставляем, над каждой стрелкой мы ставим целое число от 1 до n. Расставляем всевозможными способами.
Ага.
И суммируется по всем расстановкам.
Суммируем по всем расстановкам.
We sum up over all indices of all possible settings of indices on each arrow.
А это эквивалентно тому, мне казалось, что для этих обычных транспозиций там нумерация другая, там вершины нумеровались. Это эквивалентно, да? Такая же сумма?
Мы вершину нумеруем базисными элементами, а базисные элементы, они имеют 2 индекса.
А, понятно, да, понял.
So we just put EIJ on one end and EJI
So we put,
on the other end.
putting here I and here J, it equivalence of, so we put EIJ here, and the dual element of EJI, it's the corresponding dual element of the dual basis with respect to killing form. For example, consider a cyclic permutation. Consider a cyclic permutation. So if you put here I1, I2, I3, I4, then the corresponding element will be sum of E I1, I2, E I2, I3, I3, I4, and I4, I1. This is nothing but the standard Casimir generator C4. But this is here, it's important here that the cyclic permutation is just the standard one with the corresponding orientation of ordering of points as on this picture. If you put a different order, for instance, if you put something like that, then the result will be different. It's not equal to C3. The product is taken in different order. So now I said that this element belongs to the we consider the left-hand side as an element of the universal evolving algebra for GLM. So let me explain what is this UGLM. So we can define UGLM even without defining the Lie algebra itself. Is a algebra generated by by the symbols Eij, where ij runs from 1 to n, which are subject to relations. And the relations, the commutation relations for these generators, the algebra is not commutative. The generating relations are as follows. If you take product of two generators and multiply it in different order, then the result will be just a linear combination of generators. It will be EIL with the coefficient 1, either 1 or 0, depending on where the J and K coincide or not. And minus IL and minus delta Kj, Li, E, J, K, J. So now let me pass to the case of Lie superalgebras. Now in the case of GLMN, what's Lie algebra GLMN? We still have the same collection of generators, but now we have the set of indices run from 1 to m plus n. So we have an element of GLMN is represented by m plus n times m plus n matrices. But the set of indices is subdivided in two collections, when I runs from 1 to m or from m plus 1 to n. The first, the collection of indices between 1 and m are considered to be even, and the remaining indices are considered to be odd. So we have a Z2 grading in the space where this matrix is acting, and we have the corresponding indices. And the commutation relation in Lie, the universal enveloping algebra of this superalgebra GLMN is defined again in a similar way. The generators are also labeled by the same collection of generators, m plus n times m plus n generators, but the commutation relations are slightly different. Namely, we use the following agreement. So I will put the over bar, which means the either 0 or 1, when if it is the corresponding index is odd or even or odd respectively.
Meaning what? So even means that I is between 1 and n.
It's
In and m, yeah.
Yeah?
Ну, четный — это когда и между единицей и m.
Yeah. Yeah, and this are treated as element of Z2. So we put here a certain sign.
Ну, я просто подчеркиваю, что четное не в том смысле, что делится на два, в том смысле, что yeah,
the name.
the name.
So we put here certain sign, and the sign is -1 to the power I plus j times k plus L. And the same sign is put here, -1 to the power L plus I plus j times k plus L. So depending on the parity, we sometimes put minus here, sometimes plus. And it proves out that in order to define an element which belongs to the center, we put here also a certain sign. And the sign is certain polynomial. So sigma is a permutation, f sigma is a polynomial, degree 2 polynomial, quadratic polynomial, in the set of indices I, j, k, and so on, which participate in this sum. And if we put the sign in a proper way, then the statement that the result will belong to the center of this algebra. So they will be commuting in the very naive sense. So just commuting without any sign, without any additional sign. So let me explain the rule for this sign. So we have a permutation represented by a graph directed graph. We have the set of edges which indicate the action of the permutation, and the corresponding labels. And our goal is to define this sign function. So this function has two summands. And the first summand is linear. The linear function that we should take the sum of indices AA, and each index appears in this sum either with the coefficient 0 or 1. So we should put sum of not all the indices, but those which appear with the coefficient 1. So what are those coefficients? What are those edges which appears with non-zero coefficient? And these are exactly those edges for which, if you look at the edges, they're directed either to the left or to the right. And we take exactly those which are directed to the right. So we take those edges which are directed in the graph to the right, and take the corresponding indices with a coefficient just 1. And those which are directed to the left are taken
The
with the coefficient
The
0.
notation is bad.
Hmm?
Sorry, the notation is bad. You should use another letter. Yeah, here.
So this is I label the H.
Let it be alpha.
H, this is an HA, and this is a label which is ascribed to this.
Nope. IA is the first argument. So it's okay.
Okay. And then also there is a second summand, which is a quadratic. And this quadratic summand is defined as a product of EA times EB over certain collection of pairs of edges. So we should indicate again which pairs of edges are taken with the coefficient 1. So let me denote this coefficient which stands in front of A and B by the linking number of the corresponding edges A and B. So linking number takes the value either 0 or 1, and the product of the sum over all unordered pairs AB of edges. So now I will indicate, let me show the table which shows in which cases the linking number is equal to 1 or it is equal to 0. So in the simplest case, we assume that these two edges have all 4 endpoints distinct. Then this could be, the endpoints could be either как-то перемежаются.
Interlake.
Alternate.
Alternating, yeah, or not. So if they are alternating, we put the linking number 1. If they are not alternating, then the link number is 0. But there are also a possibility when the corresponding two chords have two common edges. Something like that. Or like that. Or like that. Then the corresponding value of the linking number depends on the orientation. And let me show the table. Now this is the definition, and mnemonic rule is the following. So since they have no common edges, we should bring it to a general position by slightly shifting the endpoints of the arcs at the common point. So since this is a graph of a permutation, at the common point, one of the edge is incoming and another one is outcoming. So the rule is as follows. So whenever we have an outcoming edge, we put it a little bit to the left. And if you have a the starting point is moved to the right. Yes. The starting point is moved to the right. The starting point is moved to the right, and end point is moved to the left. So the starting point is moved to the right, and the end point is moved to the left. Yeah. So let me check this rule for the other cases. The starting point moves to the right, the end point moves to the left. Yes. So after the corresponding correction, this is equivalent to this one, and this will be equivalent to starting point to the right and end point to the left. Yeah. So they will be alternating. And here is the same, starting point to the right and end point to the left. So they also virtually alternating. So the diagrams on the left-hand side are considered as being virtually alternating, and these are virtually non-alternating. So this is the rule, and probably let me add one more case when it is considered to be zero if this is a two-cycle. If it is two-cycle, then the corresponding pair of edges, the linking number is assumed to be zero. But this is included by this rule. End point to the right, starting point to the left, end point to the right. So, no. If you apply this rule, then this will become alternating. But however, in this case, we assume that the link number should be zero. Okay. Now let's consider certain permutation and certain fragment of our graph. So if you put
these are two neighboring points.
Two neighboring vertices.
Number K and number K plus 1. Yeah.
And we put certain indices here, I, J, K, L. Putting these indices means that in the corresponding definition of this invariant, in the corresponding product, we will have EIJ, EKL in this order. EIJ corresponding to the left vertex and KL corresponding to the right vertex. Then we subtract the graph corresponding to these two vertices interchanging.
So what Maxim is now doing, he is trying to write down the
The-
four-term relation, the analog of
Not for well, the relation, the inductive relation for
the
this,
inductive relation for computing
for computing this invariant.
Computing this invariant, yeah.
So ij and kl. So here the product. So we have the product of some other elements, but here we take these elements in the opposite product, ekl and eij. So if you take the difference, so in the case of GLM, in the usual case, non-super case GLM, this difference should be represented as here. And what's written here? This is an element connecting EIL. It means that this will be IL. This is a permutation which is represented by this diagram. So it has the degree is one less. The degree is one less. Two neighboring vertices are replaced by one common factor, one common point, and J and K are assumed to be the same. So J and K assumed to be the same. So we assume that K and J are the same. And since they are the same, we have EKL, IL, and when we sum up over all possible collection of indices, if the corresponding term appears as many times as we have many pairs of indices k and j which are coinciding. And this term appears n times on the right-hand side. Just because for different values of the indices, of the common indices, we have just the same expression. So this coincidence of indices j and k in the sum appears just n capital times. And there is also another term corresponding to EIL, and we have here delta kj, but we sum over all possible tuples of indices k, j, I, and l, so we gain this coefficient. And also, there is another term which appears with a negative sign, which corresponds to the appearance of EKJ, corresponds to this summand of the relation. And there is also the contribution of this one, which is just, oh, sorry. I missed two appearances. Okay, delta kj, IL. Forget about the coefficients. I was convincing, but I was wrong. So this is the relation. So another form of this relation appears in the case if by chance we have two neighboring indices in this product coinciding. So consider the case when we have a permutation of the following form. Well, I would prefer switch the order of these two summons. I, J, and K minus I, J, and K. So what do we have here? So E, I, J, E, J, K. And here E, J, K, E, J, K, E, I, J. So when we apply the commutation relation, what we get on the right hand side? So we have sum over all possible J delta Jj, which is just equal to 1. And this is just the capital N. And E is the corresponding term which corresponds to the IK. So these 2 points collapse to one single point, and we have a smaller number of permuted elements, and minus delta IK, and what we have EJJ. E delta IK EJJ. So delta IK means that these two strands are connected together to, and we have that I is equal to K. And this I equal to K appears here, and this sum over all J, sum over all J is nothing but the element, the Casimir element, which is corresponds to the trace. It's just C1. So these are the two recurrence relations which are used to compute our invariant. So these relations allow one to conjugate the permutation by a transposition. We put two neighboring, it allows one to exchange two neighboring points in the graph of the permutation. So we can, after some number of steps, we can reduce it to the product of several independent cycles. And each cycle is each cycle of this sort represents the Casimir element. So we have
these are not just independent cycles, but these are standard cycles.
Just product of standard consecutive product of standard cycles.
Independent cycles, yeah.
So let me show an example of this kind of computations. So consider a wrong cycle. consider a wrong cycle. To make it standard one, we could exchange two of the vertices. For instance, let's exchange, well, these two vertices. So what we have, this is the standard C3. And on the right-hand side, we will have some combination of terms which have smaller number of indices. So we apply the second relation. So we get n times this one, which is just C2, and minus C1 times we just erase these two vertices. When we erase these two vertices, this is just another copy of C1. So this is, so we get that this one is equal to C3 plus n times C2 minus C1 squared. Is that correct? So I put should minus. This is minus, and this is plus. And why it is so? So I should put also correct signs here as well.
On the left, you have an opposite difference. Yeah?
Ah, okay. So the disappearing edge is from the left to the right. Mm-hmm.
And then restore the signs on the right.
Yeah.
Great.
Now, what happens?
And then it will be C3 minus n times C2 and plus C1 squared.
The 3 minus n times plus C1 squared. Okay.
It will be okay.
Now, what do we have in the case of the Lie algebra GLMN? So we have 4 diagrams in this relation, denote them by sigma, sigma bar, sigma prime, sigma bar, and sigma bar prime. So we have in the corresponding sum, we should introduce certain signs. So minus 1 to the power of f of sigma, f sigma. So here we have minus 1 to the power f sigma bar, minus 1 to the power f sigma bar, sigma prime, and minus 1 to the power f sigma bar prime. So let's compare the signs. The signs will be different slightly. The correction signs will be different. So to the very same chord diagram, there corresponds to different signs with some with different signs. So how the corresponding signs affect, how these signs affect the formula. So, of course, we cannot compute the signs directly because the signs depend on the. So here is the definition of the sign. The sign depends on the behavior of other chords which are not represented in this picture. Instead, let's compare the change of the signs. So let's compute F sigma minus F sigma bar, for instance. So for the first, two diagrams, so we should compare the linear terms and the quadratic terms. The linear terms, so there is a correspondence between the edges, so we use the same labels for the corresponding edges, and we use the direction of the edges does not change, so the linear terms are the same. All the corresponding edges have the same directions. So the linear terms on the left-hand side and the right-hand side are the same. So now let's compare the quadratic terms, which corresponds to the linking number. So the linking number on the left-hand side and on the right-hand side for this diagram and for that diagram. Of course, this linking number does not change if it involves two chords which are not shown on the diagram. And also, neither it is involved if we have just one chord of those shown on the diagram and another one which is not shown on the diagram.
By sigma bar, you mean sigma prime here, or?
C prime, yes, prime. So if you have some other chord, which are probably linked or not linked with that one, which this will be also linked with the corresponding chords here, because the other endpoints very close to this one. The linking number between this chord and that chord does not change. So the only change, the only difference could appear for those chords that appear in this picture. But on the picture we have 4 different chords. 4 different chords constitute 6 pairs. So we have 6 pairs of chords, and for each pair of chords we should check whether the linking number is preserved or not. So if you consider, for instance, the linking number of the chords I and J on the left-hand side and on the right-hand side. So we apply this rule by resolving the point in some way, but it's clear that we will apply the same rule for both cases. So independently whether these 2 chords are linked or not, they have the same property for this picture and for that picture. So the pairs I and J and the pairs K and L are not involved neither to the left-hand side nor to the right-hand side. So let's check other pairs of chords. For instance, let's take I and L. So you see the endpoints exchanged. So the linking number is changing. If it is linked on one of the diagrams, it's not linked on the other diagram. So the difference is certainly involves I and L. And by the similar reason, it also involves K and J. And also it involves what it does involve. If you take K and I also, the endpoints. And also it involves K and I, J and L. So among those 6 pairs of chords, 4 of them changing the property of being linked, and 2 of them just preserve the linking number. So this is, if you collect common factors. This is nothing by I plus j times k plus L. So it follows that these two summands are different by an overall factor -1 to the power I plus j k plus L. But this factor is exactly the one which appears in the definition of commutation relations in the superalgebra GLMN. So it follows that if we introduce the signs in the definition of the corresponding value of GLMN invariant associated to these two permutations, then these two permutations represent exactly the difference that appears in the commutation relation. Just the very same factor. And then one could check in a similar way the contribution of the other vertices, and they appear exactly like here. So the corresponding coefficient that appears here is just 1, and here just -1 to the power I plus j and k plus L.
So, Maxim, I is the arrow entering the left point, and J is the arrow leaving the left point. Can we consider I plus J as the parity of the point for a given choice of indices?
This is exactly what this relation says.
Yeah, I see. Yeah.
So these sums are the parities of the corresponding elements of the Lie superalgebra. It's amazing that, for instance, if we apply the same analysis to the other pictures, so for instance, we denote here sigma prime, sigma bar, and sigma bar prime. So what's interesting that here we have, instead of 4 indices, we have 3 edges. 3 edges. But what's interesting is that the edge corresponding to the index j changing its orientation. So the corresponding difference in this case will involve also the linear term, just j. It corresponds to the contribution of linear terms, as here. So this bottom one is changing orientation. But also, on the other hand, all other 3 pairs of indices, ij, jk, and ik, change their linking number, so they are involved in this sum. So ij plus jk plus ki. But it's peculiar that this sum also factors in the same way, I plus j and k plus j. So I plus j corresponding to this
This is
factor,
the difference.
j plus k corresponding to this factor.
This is the difference between.
Just because g squared has the same parity as j. So we have just the same factor here, the factor corresponding to the commutation relation between these two elements, minus 1 I plus j and j plus k.
Do you really mean that it is between the diagrams or between the, or in the next row? Это действительно между диаграммами или между ЕИЖТ?
Чего?
Этот коэффициент должен стоять в этой строчке или в следующей?
Здесь, конечно, да.
И минус перед ним. I bar plus j bar j plus k, yeah. J plus k. Yeah, this indices. I jk old bar. And by the same reason, one can check the appearance of signs, and one should introduce the sign j here, which corresponds to correction of C1, just because of this orientation of this edge on this case. And also we have minus 1 to the power j here, which corresponds that the sum is not n anymore, but the difference m minus n. And probably finally, let me give some more. The time is over. Let me show the answer for the. 20 minutes ago. The time is over 20 minutes ago.
So, yeah. So if we consider such permutation, the standard cyclic permutation, in this case, there is this is I1, this I2, I3, I4, IK. So the linear term of the sine function is there are only those arrows contributes which go from the one left to the right. So we have minus 1 I2 plus IK, and I1 goes from the right to the left. And all linking numbers, all virtual linking numbers are 0. There is no quadratic contribution, and I1, I2, IK, I1. So this is an expression for the Casimir element in the case of GLMN. Okay, let me stop here.
Okay, thanks, Maxim. Are there any questions, comments? Там бары еще нужно.
Yeah. Thank you.
In the usual case, yeah, just the product. Yeah, just the product.
In
And,
the usual case, all bars are considered
yeah,
to be zero.
and, this was probably the most complicated part of the research, to put a correct sign. It was most complicated, but the answer is beautiful and rather unexpectedly, what we see is that the superalgebra, Lie superalgebra invariant doesn't provide new information because it results as a specialization from GLN by substitution n equal to the difference m minus n. Both things are unexpected. The first thing is that there is a universal invariant which covers all GLNs, and the second one is that the super version covers can be extracted from the standard version. And in fact, I'm not quite sure, but it looks like that each Lie algebra can be faithfully represented in some GLN, finite dimensional. Yeah, and so if we know everything about GLN, then we know everything about all finite dimensional Lie algebras together. And the same for Lie superalgebras. It looks like. Now we have an efficient way to compute these weight systems, and one can also hope that it can be written in a not invariant, in efficient computation of the corresponding not invariants rather than just weight systems.
I would like also to know that the result was obtained somehow observed experimentally. So Joke just computed by hand this invariant for the first several dozen of core diagrams, and then he observed that just it reduces to the substitution and capital is equal to m minus n. So probably now it's time to make the same experiments for other classical series of Lie algebras, ON, SPN, and so on, of B, C, D series.
Yeah, but there also must be some specializations and well-known specializations, I believe, of GLN.
Is it possible
Okay,
that
let's stop here because we do not have even time for the break.
Yeah. Thank you.
But we, at least at the moment, I can't see the next speaker. Lada, вы где?
А я, наверное, что, должен остановить трансляцию и снова ее запустить, да?
Да, я думаю, так